Part C, we have the sum n equals 0 to infinity, negative 1 to the n times 2 to the 4n divided by 2n plus 1 factorial. Notice the series starts at 0 instead of 1. Well, start out like this. I always start out the same way in these. I take the absolute value of an plus 1, subscript n plus 1 over an. I write down that generic formula, and then in terms of the an I'm given, this is an, remember, the part that comes after the sigma symbol for sum. And that tells me, oh, I've got to plug in n plus 1. The numerator of that formula I wrote down tells me I've got to plug in n plus 1 wherever I see an n in the formula for an. And that's going to be the numerator of an plus 1 over an. So let's do that. So what does that give me? Well, negative 1 to the n plus 1. This is just going to disappear anyway because I'm going to be taking absolute values. And then times 2, okay, 4 to the n plus 1. If I go ahead and multiply out, so the idea is I'm plugging in n plus 1 there in place of n. So I'd be multiplying that whole thing by 4. So what would that give me for the exponent? There you go, 4n plus 4. So 2 to the 4n plus 4. Does everybody see where that comes from without showing that work every time? Okay. And then divided by, well, what would I get on the bottom if I plug in an n plus 1 here in place of this n and multiply by 2? 2n plus 2 plus 1, which would give me 2n plus 3. And then don't forget the factorial after that. 2n plus 3 factorial. Now, if you want to show the algebra on that and just put in an additional step, like plug in the n plus 1, and then in the next step multiply things out, that's absolutely fine. But does everybody see where that comes from? All right. Now, oh, and I prematurely closed that absolute value because I have to divide by an, which is the same as multiplying by the reciprocal. So what do I end up multiplying by? Just flip this guy and multiply, right? Yeah, that's the same as dividing by that guy. So that means I've got 2n plus 1 factorial on top. What do I have on the bottom? Just, yeah, exactly. Well, yeah, you're right eventually anyway. I haven't taken off the absolute values yet, so I still need the negative 1 to the n there. So negative 1 to the n, 2 to the 4n. Okay, so that's equivalent to absolute value of an plus 1 over an. Does everybody see where that comes from? Okay, now the absolute values split up over multiplication and division, not over addition and subtraction. Don't ever try to split up. Don't ever try to write, unless one is 1 and 1 is 0, don't ever try to write a plus b is equal to, don't write this down please, is equal to absolute value of a plus absolute value of b. It's not true. You could write that down with the not equal to. But it is true if the operation is times, a times b absolute value. That is true, or change this to division, and it's still true. So long story short, we can break up the absolute value and get those the absolute value of those factors of negative 1 to the power outside, separate it from the rest of the factors in the numerator and denominator. You take the absolute value of negative 1 to a power, what happens? It's gone. Trying to make it exciting. You know, inflect the voice, make it exciting. It's hard. Okay, so, well, wait a minute. Can't we just drop the absolute values altogether in this case? And as long as we get rid of the negative 1 to the powers? Because 2n plus 1 factorial is positive, so is 2n plus 3, so is 2 to the 4n, so is 2 to the 4n plus 4. So as long as we take the absolute value of negative 1 to the power, which makes it just 1, in other words, drop both of these guys, we can just delete the absolute values altogether and write 2 to the 4n plus 4 times 2n plus 1 factorial. I'll put that all in one numerator. And then, let's see, I'm going to put the power of 2 beneath the power of 2. So I'm going to switch the order of the multiplication. 2 to the 4n here, and then 2n plus 3. Put the factorials kind of aligned together like so. And then you want to simplify. You can simplify the powers of 2 in this first step, or in this step, I mean. You're dividing like bases. Do you remember what the rule is? Same rule as, one of the laws of exponents, same rule you've been playing with since beginning algebra. Like bases, you keep the base and do what to get the new exponent? Subtract the bottom exponent from the top exponent, which leaves you with what? 2 to the 4. So the next step, let me shrink this down a bit. I like to go from left to right in these ones. So I'll have a 2 to the 4th left in the numerator, right? Kind of like that. And then, okay, I'd like to see you simplify the factorials. So what would you do to simplify the factorials and show the work, I mean? Would you do anything to the numerator yet? I would, because it's smaller, 2n plus 1 factorial is smaller than 2n plus 3 factorial, I would just leave it. 2n plus 1 factorial. But how would I want to rewrite 2n plus 3 factorial in that denominator to see the cancellation? What would I do? Write it as
2n plus 3 times 2n plus 2 times 2n plus 1.
Yeah, using the definition of factorial, 2n plus 3 times 2n plus 2 times 2n plus 1, and then I can put the factorial after that. Same thing, right? That's the same thing as 2n plus 3 factorial. And then you can see what cancels. You can see then what cancels, that guy and that guy. So going down one line, we get what? 2 to the 4th, which is, I guess, 16, over just the remaining factors, 2n plus 3 times 2n plus 2. And remember, the ratio test says we want to take a look at the limit of this thing as n goes to infinity. And if it's less than 1, then the original series converges. If it's greater than 1, the original series diverges. If that limit is equal to 1, we're out of luck. We got to use something else. So I'm going to use the arrow notation so I don't have to introduce, I'd have to do a little more writing to introduce the LIM notation here. So instead, I'm just going to go, oh, that guy, I think it's pretty obvious what that guy does. So because it's really a degree 2 denominator when you multiply this out, the degree of the denominator is bigger than the degree of the numerator, which means, and more specifically, the numerator is a constant. So you don't have to show any work when the numerator is a constant. You know the denominator increases without bound. The numerator stays the same. You know that this thing converges to 0. How does 0 compare with 1? Yeah. So what's your conclusion? So the original series there's only one series in question here, so you can just say the series. Converges, now you have to put in an explanation here. Converges by, what test did we just use? The ratio test. Now, when you're using the ratio test, you're proving, if it converges, you're proving absolute convergence by default. And it's not a bad habit to get into to write it every time. So we do get absolute convergence on that one. And that's it. That's all you need. Okay. Hi.
How did you get the 1 plus 4 in the first step?
So in over here, remember what we're doing. We're plugging in for a to calculate this guy. That's what this is. This is just an alternate to function notation. This is like saying f of a sub n plus 1 is like saying f of n plus 1 function notation wise, which means wherever you see an n, you plug in n plus 1. But you have to distribute that 4 to that n plus 1, and so you get 4n plus 4.